Hello, in this video I'm going to talk about partial fraction expansion. Why do you need partial fraction expansion? Well, often in practice we are faced with the following problem. Given a rational function or transfer function in the case of control systems, we want to represent such a function as a sum of simpler terms. For example, say that you have a function ws is equal to 1 over s minus 2 multiplying s minus 3, and we want to represent such a function as a sum of simpler terms. Let's say a over s minus 2 plus b over s minus 3. So the basic problem is to find the constants a and b. This expansion is called a partial fraction expansion. First, we are going to use a high school level approach to solve this problem. Then, we are going to use a more sophisticated and elegant approach for solving this problem. This approach is called the Haber method, and in between these approaches, we are going to explain how to compute a partial fraction expansion using Matlab. I have to mention that I have created a post that describes everything that I will say in this video, and in that post you have equations, you have derivations, you have Matlab codes, etc. I'm going to give a link to this post in the description below. So let us start with high school mathematics and let us use the high school level approach to solve this problem. So we want to represent ws as a sum of a over s minus 2 plus b over s minus 3. So what we are going to do, we are going to multiply these two terms. So we are going to write it down as these terms over here as s minus 2, s minus 3, and then we are going to have a multiplying s minus 3 plus b multiplying s minus 2. If we multiply these two terms together, and if we expand such expression, we're going to actually, if we group the terms together, we are going to obtain something that looks like this. Okay, we can check if this is correct. So we have a plus b multiplying s, and we have minus 3a minus 2b. So this is fine, this is correct. Now, this expression over here has to be equal to our original expression for ws, and we have to find unknown constants a and b such that this holds true. Now, the expressions, let's call this expression 2 and expression 1, are equal if the term in the numerators are equal, since the denominators are equal. So we have to satisfy the following equation. Okay, so on the left hand side we have a polynomial, and on the right hand side we have a polynomial. These two polynomials are equal if the terms multiplying the s terms with a certain power are equal. So here we can write the left hand side as 0 times s times 1 plus. So we can clearly see that 0 is equal a plus b, and that minus 3a minus 2b is equal to 0. By solving this system, we can obtain the solution, and the solutions are a is minus 1 and b is 1. So these are our solutions. So we have seen that we can write the original expression over here as a sum of two fractions. That's why this whole approach is called partial fraction expansion. Now, let us use Matlab to verify this approach. So here's the Matlab code used to compute the partial fraction expansion. Here I define a symbolic variable s that's used to represent our s. Then here I define the function w of s, our rational function, and I use the built-in Matlab function partfrac to compute partial fraction expansion. As the result, you obtain this term and this term. So a is -1 and b is 1. So you can see that you can, with a few lines of Matlab code, you can verify this. Now, the previously explained high school level approach might work in the general case. However, the equations become tedious since we have to solve a system of equations at the end. So is there a more systematic way to compute the partial fraction expansion? Well, there is. There is a more systematic way, and this method is called a cover method. Now, let us explain this method. So, your WS function in the general form can be represented as follows, as a basically fraction of two polynomials, of the denominator and the numerator. Now, under some mild assumptions, we can represent this polynomial, actually this rational function, as follows. We can compute this term here, where g is basically constant and polynomial in the numerator can be represented as a product of simpler terms, and the polynomial in the denominator can be also represented as a product of a simple term. Now, constants z1 until zm are called zeros. They are called zeros. Why these constants are called zeros? Well, if you compute f of, for example, z1, you will obtain 0. That is, the value of your function for this term becomes equal to 0. And the constants p1 until pn are called poles. So why these terms are called poles? Well, one of the reasons is that when your v of z, when z approaches p1, for example, the value of this function, assuming that p1 is real, will approach to infinity under some mild assumption, plus or minus infinity, right? Under some mild assumptions. I don't want to go into more details in this video. So we have to remember zeros are zeros of the function, and the poles are values for which this function is not defined or it reaches plus or minus infinity. So the main goal of partial fraction expansion is to represent the function ws as a sum of fractions. That is, as a sum of s minus p1 plus c2 s minus p2 until the nth fraction cn s minus pn. We have to mention that this expression is valid only if the poles are distinct. So the poles p1 have to be distinct from p2, from p3, etc. till pn. So when this is satisfied, there is such a partial fraction expansion. Later on we are going to show how to compute partial fraction expansion when this is not satisfied. Okay, for the time being we are assuming this thing. Notice here that p1, p2, and p3 and pn can be also complex poles. Okay, so let us now derive a procedure for computing c1 until cn constants. Well, this procedure is very easy to derive, and it's very nice. The derivation seems very nice. Now, let's see what happens if we, let's say, multiply ws with, for example, s minus pi. For example, with the ith pole, if you multiply ws, actually not with the ith pole, with s minus pi, what do we get? We get s minus pi over s minus p1 multiplying c1 plus s minus pi s minus p2 C2 plus, then we have a term with pi'd term, pi, s minus pi multiplying s minus pi in the denominator, cancel each other, and then you get ci plus s minus pi over s minus pn multiplying cn. Good. So what do we see here? We see that if we multiply the whole expression with s minus pi, this constant pop-ups. So how to get rid of these other constants such that we only are left with ci? Well, this can be achieved by simply evaluating this expression for s equals pi. So when s equals pi, these terms over here, this term is equal to 0, this term is equal to 0. Why? Because pi is not equal to p1 and the poles are distinct. So at the end we only get the ci term here. So this is equal to ci. So here is our formula. A very nice formula. That is, to obtain the ci'th constant, we take the original expression, we multiply it with this spi, and we obtain this constant. So if you want to get the first constant, we multiply the whole expression with s minus p1 and evaluate such an expression at first pole. And this is our formula. Here you can also see why partial fraction expansion is important. Say that we want to compute an inverse Laplace transform of w of s. If we had the original expression, for example, we have expression 1 over s minus 2 minus s minus 3, we will have difficulties to compute inverse Laplace transform in this form. However, if you represent this as a partial fraction expansion, so if you represent this as 1 over s minus 3 minus, actually here, minus s minus 2, it's very easy to compute inverse Laplace transform, since we know that inverse Laplace transform of function s1 over s plus p, where p is a constant, is nothing less than e minus pt multiplying Heaviside functions. Heaviside function is nothing less than a function that is 0 before 1 and at 1 becomes 1, and this function is usually used in control systems to represent step inputs, or in this representation to ensure that everything what happens before 0 is not taken into account. So if we have expression ws that is expanded using partial fraction expansion, we can simply compute inverse Laplace transform just as a sum. This becomes as a sum, you obtain a sum, I is 1 to n, ci constants, e to the minus what? E to the plus, actually, p I t. So this is our expression. Okay, so to demonstrate the application of the partial fraction expansion, so let us solve this example. So the example is compute the system step response, where the system is given by the transfer function w of s. So what do we have here? We have a system, or our transfer function. Here is the block diagram, and we say, okay, we are going to put as an input a step signal, and we want to see the output, how the system will behave, how the output of the system will behave. For example, it can be like this, it can oscillate, or it can exponentially move, or however, right? We don't know that before we compute this. Actually, we can figure out how the output of the system will look like by looking at basically the poles of the system, but let's leave that for the next video. So let's solve this example. So how we're going to solve this example? Well, we're going to use partial fraction expansion. So let us apply partial fraction expansions. So we want to represent g of s, which is your system's response, as w of s times 1 over s, where 1 over s is the Laplace transform of the Heaviside function. This is your input, right? So your output of the system will be y of s will be equal to g of s, and this will be equal w of s multiplying 1 over s. So we are having here s plus 1, s plus 3 over s plus 2 multiplying s plus 4 multiplying s. So we want to expand this function using partial fraction expansion and then to compute inverse Laplace transform of all the fractions. So what do we have here? We have c1 over s plus 2 plus c2, let's say s plus 4 plus c3 over s. Okay, so why can we apply this formula? We can apply this formula because the poles are distinct. So since the poles are distinct, we can apply this formula. So let's compute c1. So how to compute c1? Well, we take g of s and we multiply it with s plus 2 and evaluate such expression at s equals to minus 1. So what do we have here? We have s plus 1, s plus 3 over s plus 4 multiplying s, right? And we evaluate this as at s minus 2. So what do we have here? We have minus 1 multiplying 1 over minus plus 2 multiplying minus 2. So what do we have here? We have 1 over 4. So let us compute c2. c2 is equal to g of s multiplying s plus 4 evaluated at s minus 4. So let us compute this. So what do we have here? We have and this has to be evaluated at s minus 4. So let us evaluate this expression. What do we have? So what do we get? We get 3 over 8. And finally, let us compute c3. So c3 is g of s multiplying s evaluated as 0, evaluated at the pole. So what do we have here? We have s plus 1, s plus 3, s plus 4, and this becomes 1 times 3 over 2 times 4, and this becomes 3 over 8. So our final expression is given by the following formula. So this is y of s. We want to compute y of t. That is, we want to find an inverse Laplace transform of this expression. We know that Laplace transform of the exponential function, where the pole appears over here, becomes nothing less than s minus pi. And the inverse Laplace transform is just inverse of this one. Now, what do we have here? Since the Laplace transform is a linear operator, we can compute inverse Laplace transform by computing inverse Laplace transform of every term, and the constants do not influence the inverse Laplace transform. So what do we have here? We have 1 over 4 e to the what? E to the minus 2t plus 3 over 8 e minus 4t plus 3 over 8. Since the Laplace transform of 1 over s, so we have a heaviside or just 1, the Laplace transform becomes 1 over s, and inverse Laplace transform is just 1. Now here we need to add what? We need to add a heaviside function, since we are not considering values of t below 0. Good. Now let us use Matlab to verify this. Okay, so here is the Matlab code used to solve this problem, to compute the partial fraction expansion and to compute the inverse Laplace transform. So if I execute this code, here what happens? Here's your w of s, right? We want to compute the compute basically, not W, this is G of S. We want to compute the inverse Laplace transform or the step response of such a system. Here is the factorization, compute by using the function part frac. And here's our expression. So we obtain 1/4 e to the minus 2t, 3/8 e to the minus 4t plus 3/8. And this is exactly what we obtain over here. Okay, that would be all for today. Thank you very much for your attention and stay tuned for more videos. If you like this video, please share it or subscribe or try to support this channel in some form. Thank you very much.